When you're trying to balance a redox reaction, you have to check to see if the problem is implying that the reaction is happening in acid or base. If your problem says that you're balancing a reaction that is in acid or in an acidic environment, follow these steps. The first step to any redox reaction balancing is assigning your oxidation numbers. This iron 2+ follows the rule where the ion is its charge, so it is a 2. The oxygen in the dichromate is going to be -2, but figuring out the chromium can be a little tough. So I'm going to make a little algebraic equation with 2 mysteries for the chromium plus -2 times 7 equals the total charge on the species, -2. Then I'll rearrange my algebra. This part is -14 plus 2 mysteries equals -2. Add the 14 over, divide by 2. My chromium's oxidation number is +6. Then I'll look on the other side of the reaction and I'll see my iron has a 3+ charge, so his oxidation number is 3. And the chromium also has an oxidation number of 3. Okay, now I'm going to identify which one of my interesting atoms is oxidized and which one is reduced. To be oxidized, you need to be losing electrons. Your charge would need to go up. And we can see pretty clearly that my iron species goes from a 2+ to a 3+. So I'm going to write down ox for oxidation, and I'm going to write down the half reaction for that, which is iron 2+ goes to, or yields, iron 3+. I'll balance that in just a moment. Now let's handle the reduction. The reduction half reaction should be gaining electrons, so we'll see my oxidation numbers go down with those negatives being added. So that's the chromium. The chromium's number goes from +6 to +3. Okay, so I'm going to write down those species as well. I'm going to write small because I feel like I'm going to need some space in a bit. You can always assume that if you're starting with oxygen on one side of your reaction, but there isn't any on the other side, that you're going to need a lot of writing room. Okay, now let's start to balance the redox reactions. Our next step is to look at our half reactions and balance the elements that are not hydrogen or oxygen. So I'm going to look at my iron oxidation bit first. Okay, so I see that I have 1 iron atom on both sides, so that one's good to go. Now I'll check my reduction. On the reduction side, I have 2 chromiums on the left, but only 1 on the right. So I'm going to add a 2 in front of my chromium on the right to fix that imbalance. Okay, now we're ready for the next step. Let's balance our oxygens using water. We know water's around because all these reactions are in aqueous solution. Okay, so on my reduction side, I see that I have 7 oxygens on my reactant side and none on my product side. So I'm going to add 7 waters to the reduction side to take care of my oxygen issue. As soon as my oxygen issue is taken care of, I now have a hydrogen issue. Balance hydrogens with H+. Now, why can we use H+? Because this reaction is supposedly happening in an acidic environment, so they're readily available. I see that I have 14 H's that I added to this reaction, so I need to make sure that I'm doing the same thing to both sides. I'm going to add 14 hydrogen positives. Okay. Now that I have my atoms taken care of, I have the correct number of atoms on both sides of my reaction, I'm going to deal with charge. On the iron side, we can see that I have a 2 plus on the left side and a 3 plus on the right side. Those positives can't change without electrons being added or subtracted. In this case, an electron left the iron 2 plus, so I need to draw it as a separate entity on the other side. As in, those two species are broken now. Okay. Now, let's consider the reduction side. On the reduction side, I have 14 positive 1s and a negative 2 charge, so that means a total of positive 12. And on the right side, I have 2 positive 3s for a total of positive 6. I can see now that the total charge difference is going to be 6. This makes total sense because my chromium species started as each of them being 6 positive, and then they both went to being 3 positive. Since they lost 3, or rather they gained 3 electrons, we're going to have a total of 6 being transferred. So I'm going to say plus 6 electrons on that reduction side. Now I'm going to recopy my half reactions and line them up so I can get ready to add. Okay, now we're almost ready to add up these half reactions. We can see that there are some electrons produced in the oxidation and that those electrons are later used in the reduction, but we don't seem to have enough electrons yet to run the second half of the reaction. We need to have 6 electrons. So what I'm going to do is I'm going to multiply the oxidation portion of the reaction by 6. That way, after we multiply, we'll have a 6 for every single portion of this reaction. Okay, so 6 iron 2s and 6 iron 3s and 6 electrons. Okay, now we're good to go. When we add up these reactions, our 6 electrons will cancel. Okay, now I just need to double check that there aren't any repeating species. Sometimes for these reactions, we'll have water on both sides of the reaction. We can cancel, or hydrogen ions. In this case, we don't, so we're good to go. Our final balanced redox reaction is 6 iron 2 pluses plus 14 hydrogen ions plus a dichromate yields 6 iron 3 plus 2 chromium 3s and 7 waters. And that's how you balance a reaction in acid.